Okay, so let's just do a real quick geometry problem. I have a rectangle. I take its area, and I divide by its base. I'm going to get its height. And as simple as that sounds, we're going to use that over and over again today. So, over here, I now have three rectangles. This one has an area of 6, this one has an area of 5, and this one has an area of 12. This time, I'm going to add up the areas. 6 plus 5 plus 12. That's the sum of the areas. I'm going to divide by the sum of their bases. So that's 2 plus 1 plus 3. This gives me 23 over 6, which is going to be 3 and 5/6. So that I can actually show you what this means on this picture here. Okay, now, what is 3 and 5/6 going to represent? In the last slide, we talked about area divided by base was going to give me the height of the rectangle. Well, here I have three rectangles. So I take their areas added together, I divide by the sum of their bases. What am I going to get? Whatever it is, it's 3 and 5/6. Okay? And so that is roughly here. What I want to try to sell to you here is that 3 and 5/6 is the average height of these three rectangles. And so if I look at this picture, I think that's believable. But the idea here is if you take that 3 and 5/6 and multiply it by the sum of those bases, you're going to get the same area that you had when you add the three rectangles areas together. So, idea here is that in general, it can be done for any number of rectangles. If you take the sum of their areas and divide by their combined widths, you will get the height of the average rectangle. Pretty simple idea from geometry. I want to extend this to what happens when we talk about area underneath a curve, whether it's approximate or exact. You take these rectangles areas, okay, which you have seen, I don't know, 100 or so rectangles there, and those heights are basically function values. Not basically, they are function values if you do them in the manner of a Riemann sum. Okay? So when we talk about height of a rectangle, we could also be talking about function values. And so the principle here is that I know how to find the area of this curved region, which represents the area of an infinite number of rectangles being added together. Okay? And so the area is found by doing the integral, in this case from 0 to 6, of f of x dx. And now the question today is, what happens if I divide by the sum of the bases of those rectangles, which is just the region from 0 to 6. Okay, and what I hope you can believe and wrap your mind around is this is going to give you the average height of each rectangle, okay, or in other words, the average value of f on this interval. Okay, so what is the average value this function takes on between 0 and 6? Same as saying, what is the average height of the rectangle between 0 and 6? Remember, we're adding up the areas of an infinite number of rectangles. So this is a powerful idea. It's a simple calculation. You take your integral, you divide by the difference of the upper and lower limits of integration. Okay, very simple calculation to do, but very powerful concept. Okay, let's do a simple example. Many teachers like to use the curve y equals 10 square root of x to curve exam scores when students didn't do very well. So you would take your exam score, your raw score, which is the x, plug it in this formula, and the y that comes out would be your curve score. And that helps students more towards the bottom of the curve than towards the top, but is a standard use for many teachers. I don't use it, but there it is. Now, doing this, the question here is, what is the average exam score on this curve? So exam scores are every possible dot on this curve, which is obviously an infinite number of them, but we can still kind of theoretically talk about this. So how is this done? Well, the average value is calculated with that simple formula, which is simple. It's the integral of your function, which in this case is 10 times, I'm going to write x to the 1/2 dx. And we're going to go from 0 to 100 and divide by 100 minus 0. Okay, so my antiderivative is going to be, let's see here, it's going to be x to the 3/2, which means I can divide by 3/2, which is multiplied by 2/3, which means I have 20 over 3, which is over 100, so 20 over 300, which I can simplify to be 2 over 30, or 1 over 15. And we're going to integrate from 0 to 100. And as my standard procedure goes, two big parentheses with the subtraction sign. All right, 100 to the 3 halves is going to be 1,000. So I have 1,000 divided by 15 minus 0. 1,000 over 15 simplifies to be 200 over 3. Which comes out to be 66 2/3. Okay, so the average percentage grade on this curve would be 66 2/3%, which is a lot better than the average grade of 50%, which is just using a straight up distribution. Okay, now there are some connections I suppose we can make with this concept. And mainly I want to point this out so that we don't confuse this with our other concept that has the word average in it. But let's talk about, okay, what is the average value of f primed of x on the interval a to b? Okay, so the average value of f primed on AB is found with the simple calculation we've talked about, which is just the integral from a to b of f primed of x dx divided by the difference of the upper and lower limits of integration, b minus a. Now, the fundamental theorem says that this numerator is going to be the same as saying f of b minus f of a. And look what you have. You have f of b minus f of a over b minus a. And up here it says that's the average value of f primed. But we know that this is also the average rate of change of f on the interval AB. So there are some relationships that are built in here that you need to be aware of. And maybe doing it one way is an easier calculation than doing it another way. But you need to keep distinct average rate of change of a function f versus average value of a function f. They're calculated differently, and you need to be careful that you don't mix up one with the other. Okay, let's do a quick proof. If you're interested, you don't have to. You can skip this slide, and once you see the slide go white, you can pick up where we are in the video. But let's prove that this value, this average value, has to exist. Okay, so here's our assumption. F is a continuous function on an interval a, b. Okay, and you have this function g, which then exists. G is the integral function. Now, what do we know? We know by the mean value theorem that for some c on the interval ab, g prime of c is going to be equal to g of b minus g of a over b minus a. Now let's fill in some blanks here, okay? What is g prime of c the same as? Well, g prime of x is going to be equal to f of x by the fundamental theorem. And so I can replace g prime of c with f of c. And what is g of b equal to? Okay, so let's go back up here. G of b is going to be the integral from a to b of f of x dx. And g of a is going to be equal to the integral from a to a of f of x dx, which equals 0. So this expression on the right side becomes integral a to b f of x dx divided by b minus a. And if I multiply both sides by b minus a, I'm going to get f of c times b minus a is equal to the integral from a to b of f of x dx. Okay? And if I look at this graphically, okay, this says that the area from a to b under f of x is equal to the width of the interval, b minus a, times the function value of f at some value c. Okay? And so therefore this has to be the average height, okay, or the average value of f on that interval in order for those two expressions to be equal. Okay? So this proves that the value has to exist. Okay, now if you'd like to try some for practice, you can try 6.5, numbers 1 and 2. Check number 1 with the back of the book, and you can check number 2 with the calculator.